Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Welcome to Schweitzer Drive. I am not the voice you were expecting to hear, probably. My name is Bryan Fazzari. I am Vice President of Marketing at SEL, and today I am stepping in as your guest host. I'm excited to be here. We're switching things up a little bit for this episode, so rather than host Dave Whitehead interviewing a guest, we're putting him in the hot seat. Over the past few weeks, we've asked listeners to send in their questions about electric power, the industry, and even Dave's perspective on where technology is headed, and we got a lot of great questions. In fact, we may need to do a couple episodes in order to make a dent in this list. Today, we'll dive into as many questions as we can fit into an hour. This will be a great chance to hear Dave's candid thoughts on everything from innovation to leadership and beyond. Hey, Dave, you ready for this?
Let's light this candle.
Let's do it. Okay. Folks, I'm not going to use your last names because some of them are just too hard for a simple engineer like me to read. I am sorry. So this first question is from Bob. Bob asks, the U.S. electric power system will grow rapidly in the next 2 decades to keep up with demand. Every state and region is working hard to expand our electricity infrastructure to make the U.S. a leader in AI, manufacturing, mining, and more. SEL works with electricity providers across the USA. What are some of the best practices you see and that we should emulate? And what technologies, business practices, or state policies work best? And on the flip side, what should we avoid?
Well, this is going to take an hour and a half to go through just this first question.
This is a big question.
There are so many things we could discuss. But let's just talk about the load growth in general that we're certainly seeing in the U.S. For example, Oncor, the big transmission utility in Texas, gets requests from what they call as large customers, industrials, right? And they're making requests. Hey, I got a big project, a data center, metals and mining, petrochemical, crypto, all kinds of other things. They put in requests. Right now they have requests totaling 137 gigawatts.
Wow.
That's a lot, right? Just to put that into perspective. Of that 137, 119 gigawatts are for data centers, right? So what is that? It's like 3/4 of that request of 137 gigawatts. The rest, though, comes out to about 16 or so megawatts. Maybe I'm a little bit off on my percentages. But it includes oil and gas, utility and government, other large loads, which could be a number of things. And in crypto is actually 3 gigawatts of requested load. Now, let me ask you, what do you think Oncor's peak current demand in power is right now?
Right now,
the biggest day they had. Peak demand.
Oh, I have no idea.
Now I put you in the hot seat.
Yeah, this is not how this is supposed to go, Dave.
Yeah, I know. It's kind of fun the way I'm doing this. let me help you out then. Is only 31 gigawatts. So they have a request for 137 gigawatts. Their peak, their best day, what they had to produce was 31. If they took out the data centers, right, altogether, drop that 119 gigawatt load request and just try to do all the other stuff, right, it would be 60% increase into their peak demand. That is just Texas that we're talking about. Now we go to the rest of the parts of the country, you can just see what the demand is. And we're seeing that in our sales, our bookings, right? We had a fabulous year. Our data center is probably 100% year over year growth with all the various products we're supplying to those things. So there is a tremendous demand, certainly led by data centers right now, for electrical growth. One of the things that we were particularly aware of or cute is since there is so much demand, how do you go about speed and scale? So working with our customers, when we're talking about best practices or what we can do, it's how do we design our equipment, our solutions that drop into, a data center or a control house that's outside a data center, serving those data centers to make our our customers' lives easy. And we're spending a lot of time, not only with our present products and our solutions engineering services to do things like that, but also future stuff. In fact, we've got into we'll call it a new line of business. We call it substation engineering. The variation is engineering procurement management stuff. But to the fact we're pretty well known as a relay company. We build these blue boxes, but we also have our services group folks that are pushing dirt, pouring cement, dropping transformers and into substations and then testing them out. I like to think that, we're a very unique company. There's probably not a lot of us around that one day we're pouring cement, the next day we're changing code in a relay to take care of some new challenge that we saw. So that kind of sets the landscape for where everything is going. I think the part of the question is, what are some of the best practices that we've seen going on? And that's a really broad question, I think, right? Because there's the narrow stuff for what's our best practice for protection, or how do we automate things and whatnot. And I'm gonna say the best practices that we've seen, especially when we're doing large scale stuff, is how do you standardize on stuff? We've had the ideas of standard panels and standard solutions, standard products, and stuff like that. I think and the utilities realize this, right? They're very, very smart folks, right? The more they can standardize stuff, the easier it is to build, maintain, support products and solutions throughout their entire service territory. So I'm a big proponent of standardization, with the one caveat though is keeping an eye out for innovation too, right? You don't want to have your blinders on. It's like, that's not the way we do it here, so I'm never ever gonna look at something new. We've come out with new technologies, like whether it's SDN or time domain technologies, right? Which is not how we used to do things, right? But there are some tremendous advantages when we talk about cybersecurity, or one of the ways that we're Encore and others are creating a bunch of new power, especially we'll use Encore as our example here, is out in West Texas. They generate a lot of electricity through wind. Wind are these inverter-based resources. These inverter-based resources are really capacitors and power electronics that supply electricity into the grid, versus our traditional sources where Encore may have some coal plants that have these big spinning machines. So we've talked about rotational mass and IBRs before, and the challenge is there's a problem on the power system. The traditional big spinning mouses would kind of keep everything glued together. It was hard to slow them down and, whatnot when there was a fault, which is what happens when there's a fault on the power system, or speed up depending on where you're at on which side of the fault. IBRs don't have that kind of inertia built into them, right? And we saw the challenge in Spain where they were almost 100% renewables. They had a little bump on the power system, but because they didn't have that big inertia, those traditional rotating masses, all they had was a bunch of these IBRs and solar panels and wind and stuff like that. It was essentially the cause of the blackout, right? So things that SEL has come up with, getting back to keeping your eyes out for new ideas, is this traveling wave, time domain, and incremental quantities solutions that we've came up with. And so these technologies that detect faults quickly, right, don't rely on these big spinning masses or the sources of what we like to say IBRs or the traditional generation. Rather, the fault itself sends the information to our relays to allow us to detect faults. So I don't care if there's an IBR or a big rotational mass. The fault is telling me what's the problem on the power system. We can go and use that technology. Now, it's different. It's not what we've been using for the last 40 years in power system protection. So when we get back to best practices or new ideas, it's really important to keep that open mind and not say, well, we've always done that. So we've got great solutions, standardize on things, but keep an open mind for new technologies, especially when you have let's call it a new problem that has to be solved.
The last part you've not answered is and what should we avoid? So you described some pretty incredible growth statistics.
Well, you're skipping over the politics part. Let me go back just a little bit on that. Right, it's like policies and whatnot. And I'm not going to get political, in a sense of D's or R's or anything like that. Rather, it gets back to keeping an open mind. Politicians have a lot of aspirational goals, which I think are all really, I'm never going to argue with the aspiration. We should have clean, green energy, right? It's like, well, who doesn't want clean, green energy, right? I think we need to be a little bit pragmatic, right? And can I use coal to be green enough to delight you. Maybe not, but there are ways to make coal even, as green as perhaps possible. So having these aspirational goals with no connection, right, to physics and engineering and economics is a big mistake. Washington State, we have a challenge where we want to be, hydrocarbon free by 2050, 2040. So there are a lot of mandates that we have, like no new gas, right, going forward. So even in your home, you can't have a gas stove, right? So there's a bunch of challenges. I was talking to some folks, I think, out of Puget Sound Energy, right? And there's a lot of gas that is used to create electricity and to heat homes, right? Gas heaters. I think that the math they said is they need to triple. So everybody listening, you can fact check me, send me the notes, but I'm directionally correct, right? When I talk about the enormity, I may be off by a factor of 2 or 3, but they're going to need to triple the amount of electricity they import to keep houses warm in the winter
because of that
no
decrease in gas. Wow.
Correct, right?
Okay.
And it's like now the engineers, the economics, right, and the physicist in me goes, how the hell do you do that, right? So I understand the aspirational goal. Who doesn't think it's a good idea? It's like, I don't know how to pay for it. I don't know how to, and then we get the other thing is like, who's going to want another 500 kV transmission line in their backyard? We have that whole hurdle that we need to get to, right? So when we talk about policies, I think these policies that we're creating need to be based in engineering, science, and economics, right? They can't just be aspirational.
Right. The art of the possible.
I'm really good at coming with great ideas that can never be implemented, right? And that does nobody any good. Maybe that was what should we avoid? These aspirational objectives without the science and engineering and the economics all rolled into it at the same time.
It seems like there's a sense of urgency, or the word, I don't know if unprecedented growth is the right term to use here, but it's significant growth, and people they're starting to get a little creative about where their energy will come from, especially even with the data center growth that we're seeing. So when you're in a hurry, or when you feel like you need to solve a problem fast, you mentioned speed and scale, you can start to get pretty creative about how you approach those things.
We've seen that in the news, right? These big data centers, right? These gigawatt plus data centers. I've heard 10 gigawatt data centers now.
That's amazing.
They're going to build their own power systems and forget about hooking into the Encores or the Avistas or the Puget Sound Energies. They're going to do their own thing, right? And eventually, 2 or 3 years, when the utility can get around to connecting to them, they finally will. So that's how creative our some of our data center customers are getting.
That's interesting to watch. All right. Anything else you want to hit in that one? That was a big question.
I'm going to take a glass of water. I think I talked too fast and got too excited.
I'll give you a break. Question 2 is from Jesse, and it's related. I would love to know the answer to this question. How much is the data center industry in America going to grow in the next 5 years or 10 years? And maybe an easier part is, how's SEL going to keep up with it?
So 10 years is like forever, I think, in data setting years
time.
Or AI or, GPUs, and who knows what the next GPU is going to be. So I'm going to avoid the 10-year question.
Okay.
5 years.
To 5.
5 years. We're looking at some of the growth. Going back to Encore or a little bit, right? They would have to do 4 times growth, right, to meet their connection requests they have. Our data center growth business is probably doubling again next year. So I see a lot of growth. So the next 2 or 3 years, I think there's going to be a lot of investment in data centers and, so some other things. We have also going back to a little bit of politics is the electrification of everything, mandates on EVs, and we'll see where that ends up, right? But everything is getting electrified. Forget about the policy or, policies for a little bit. Everything is using more and more electricity. So we're going to see steady growth, I think, certainly for the next 5 years. We have a lot of our industrial friends come visit us, and we talk about what their plans are, what our plans are. We'll go visit them. Most utilities will be along these same lines. Certainly ones I've talked to, the big IOUs in particular, where they told me that they were ecstatic if year-over-year growth was 1.5%.
Yeah.
And that was typically what I saw for my 30 plus years working in the industry, right? Just about 1.5%. Sometimes it got lower than that, right? There were some lean years where they just didn't grow. The load growth wasn't there. Probably like 2008 timeframe with the housing, and the crisis that we had during that period of time. But 1.5%, and we were busy when it was 1.5%.
Right.
So now I have a bunch of utilities I've talked on the East Coast and other places. They're saying they expect like 9 to 10% year over year growth.
Something they've never probably experienced.
These folks are freaking out. It's like, man, we were busy when it was 1.5%. Now we have to do 4 times that. It's like, wow, that is a lot of growth for a utility. So that's what our large IOU customers are projecting. And I, based on our financial projections, everybody's doing planning at the end of the year, looking at, who's going to be buying what or which projects are going to be going on. I am very confident, right, that those utilities will be, growing at 9%. Of course, the big question is, we can build substations, we can build transmission and whatnot, but where are we going to get that electricity from? Right. We just said, certainly in Washington State, we're not gonna approve any gas peakers, right? So there's not going to be any gas turbines that are coming online in Washington State. I'm a little bit reluctant. It's a very cloudy day, right, to rely on solar. In fact, today I don't even know if the wind's blowing, right? So we're not getting into that. It's a good thing we got some dams on the Columbia River and the Snake Rivers right now to make, record this podcast. But we're going to need some more reliable, dispatchable energy resources. And, if you had to ask me to go beyond that 10-year period, maybe a little bit longer too, to have reliable dispatchable power, you need nuclear. I think you end up there. We've done a handful of nuclear podcasts. You go listen to those. They're out there on, I don't know, wherever you get your podcasts
all
at right now.
Yep. Yeah, all over the place.
There's some great podcasts on that. But that's going to take a while to get us to an all nuclear future. So what do you do between now and then? And I'm a pragmatic person. I'm practical. I think it has to be gas, and there'll be some solar and other things mixed in there. But on a cold day like this, if the temperature should plummet, right, we're going to need more electricity to keep our houses warm. So we're going to end up using gas, I think, and that's our most viable dispatchable energy source right now.
Yeah, that makes sense. You mentioned the Spain blackout, the Brazil blackout. The loss of inertia in general is I don't say it's an unsolved problem. We have solutions for that, but that's a challenge that arises as this continues to occur. And so, like you say, you're going to have a resource like gas involved in here.
Yeah.
Okay. All right.
Or we could build more dams out here, right? I'm happy to do that too. Right?
Or we could do that. Yeah. Okay. Question 3 is from Trevor, and Trevor asks, how do you balance meeting the needs of existing industry or existing customers with development of new technology? How do you do both?
So in a perfect world, our development folks would spend about a third of the time just keeping products up and running, because we've been in business for 40 years. We have some old designs. Customers still love them. They want us to keep producing them. And that's fine, right? But the challenge is it's got a lot of old design stuff in it, right? Some of our manufacturers don't want to build a particular part of a resistor. So we have got folks who say, okay, well, if I can't get that resistor, what do I have to do to design in a new one? So that probably takes about a third of our time. The next third is customers have some of our newer products, love them, but man, could you just add one more feature to it? So they add features to the product. And then we got a third of our time. It's just like, let's do something brand new, right? The next generation of whatever it is, a relay, a computer, automation controller, overhead wireless switch. So we want to be a little bit disciplined, right, in how we allocate our time, because we don't have infinite people or infinite dollars. We have to do some planning and some judgment calls. And you know what? That's probably one of the hardest things you have to do, right? Because, man, I want to build everything, right? I'm an engineer at heart, or the folks over in the R&D buildings.
It's all awesome.
Used to say I was an engineer. They don't call me an engineer anymore. They make fun of me more often than not. But it's one of the harder things to do as a manager. Is like, how do we allocate resources, right, to delight the most amount of customers given the resources that we have at any one time. I don't have a magic, Ouija board that tells me what we should build this day or the next day. We do have a lot of smaller people that we sit around and collaborate with on talking about new technologies. Where do we think we make the most impact with how we spend our R&D development dollars? And so far for this last 40 years, it's worked pretty well.
There's a quote from Henry Ford that I like. It's in How to Win Friends and Influence People, for those of you that have read that book. But that quote is, if there's any one secret of success, it lies in the ability to get the other person's point of view and see things from that person's angle as well as from your own. And when I was in product development, the twist I would put on that is now figure out what that person's viewpoint will be in 10 years and solve their problem.
Oh, yeah.
See if you can do it. And that's an awesome challenge. That's a lot of fun.
Then you got to convince that person you're talking to in 10 years that will be their problem.
Yeah, exactly.
That's even harder.
Right.
You can see what their problem is, but do they?
Yeah. Interesting part of inventing the future here. And it's a fun part of the job for sure. Challenging part of the job. Okay. Question 4 is related. And it's, how do you stay up to date on the latest technology to ensure SEL stays on the leading edge? And I have a twist to add to that.
Okay.
How do you choose which ones you're going to stay away from?
Ooh, which technologies I'm going to stay away from?
In our industry.
I don't know if I'd stay away from any, right? I take that as I want to understand it, right?
Right.
I want to understand all the technologies, because if I don't really understand it, then I can't say, you know what, that's just not for us. So I would say I'm not afraid or would stay away from any technologies. But, you asked me, what do I do to what I think stay up to date? It is, I read a lot, right? I talk to a lot of industry people. I go to conferences. We'll talk AI. AI, starting really probably the end of the year before 24, the end of 23 or something, was a big deal. People were starting to talk about it. I took a online 6-week course at MIT on AI, right? From the how it works, the economics, applications and whatnot. So that there was a kind of a way. I got curious about AI. It's like I'm a golfer. I'm not a great golfer, but in golf, the one thing that can really help you out is this idea of tempo, how fast you take the club back, and then how fast you transition to bringing it through the ball, and then finishing your swing. And there's some ratios to it. And I have this app on my phone that goes, it's like a metronome, dun dun dun, right? And I'll play that to try to get my head into this idea of tempo, but it's like, I really don't know if I'm doing it right. That the song's going off in my head, but my body could be doing all kinds of different things. And then I remember my Apple Watch has an accelerometer in it.
Okay.
Right. And so the accelerometer can measure the speed and distance. Really what I need is the timing. I want to know how long it takes me to go back and how long it takes me to come forward. Right. And there's this like 2-to-1, 3-to-1 ratio you want to be hitting. Right. And I said, well, why don't I just write an app to do that? Right. And first thing is, what do I know about writing apps for my iPhone that's going to go to my watch, right? Connect everything and then tell me what that timing is. So I got up one Saturday morning, everybody's still in bed. I got up on my computer or probably my iPad and said, I don't know if it was ChatGPT or probably was, right? Write me an Apple Watch app that can measure, take accelerometer measurements and put them into a time scale so I can write this thing. And it said, okay, let me think about it. And I said, I need to tell me what the development kit is and, how I can get this up and running on my iPad. And it came back with, okay, go download this software development kit. Here's the code you need to activate the accelerometer in your watch. And literally within 15 minutes, I downloaded all this stuff and I compiled the program. I got an error, right? From the program. So I copied the error back into ChatGPT and I said, hey, this is wrong. I got this error in your code. And it came back as like, oh, you're right. I'm sorry. And gave me the right code for it. I put it back in. I literally, in a half hour, I had this accelerometer programming running on my watch, right? And if I had tried to do this from scratch, I'd probably still be working on it. Now, here's the problem, right? And this is the challenge everybody's going to have with AI, I believe anyway, is I really had no idea what was going on, right? I don't know what the program calls were doing or anything like that. So it's still going to take me a long time to, I understand exactly what's happening in the program. So while it can write it for me really, really quickly, give me a really good result, I think, but I don't know all the corner cases, when it's going to work, not going to work. So would I do this for developing a power system algorithm or something like that? probably, because I understand a lot of power, about power systems and programming and stuff like that. But you got to have some context when you're going to use these new tools, right? So that's the other thing
Right.
that everybody needs to learn too. It's like when to use a tool, when not to use a tool, what's it good for, when's it not good for, when can you trust it, when can you not trust. So that's an example of recently of me trying to keep up with some trends. I know in R&D right now we're using it for a handful of different activities to speed up productivity and get more stuff done with the same hours in the day.
Yeah, it is. It is tempting to want to spend some time here talking about how this is going to change the scope and requirements of software engineering or firmware development. But maybe that's a deep topic for another
time.
All
these questions and had AI write answers.
For all I
right?
know, that's what you've done.
Here's a bunch of papers that Dave wrote, right, and emails and stuff. Respond to these questions then.
Okay, this next question is from Travis. There's been an increase in solar activity the past few years. I think 2025 is the peak of the solar cycle, if I'm not mistaken. We witnessed recently with the incredible northern lights. A bunch of people saw it way further south than normal, and a prediction for an upward trend in solar activity in the future. This increased activity can affect our electric grid systems and knock out communications and all electrical devices, such as what happened with the Carrington event of 1859, which is characterized as a 500-year event. And there's a story there about some telegraph operators from Portland, Maine to Boston, Massachusetts using that system without batteries. What steps has SEL taken to try to protect their equipment from this kind of increased activity?
So I did not expect this question. I've been involved with geomagnetically induced currents,
right.
and there's a similar event that happens with EMP, a nuclear weapon going off, and
right.
the wave it creates. So in EMP, there's they call it E1, E2, E3 waves that happen. E1 is this really fast, high voltage thing that people are really concerned about. E2 is more akin to like a lightning strike on a pole, and E3 is very similar to GMD in that it's this quasi DC current that gets induced in power lines.
Right.
Everybody references this Carrington event, right? And you're right? There were some telegraph operators. It burnt down the systems. There's an event in Canada,
Quebec. I
right?
know where you're going.
And it was like in the 60s. I think there was a GMD event that caused some relays to misoperate, trip out, and really black out the Quebec area, if I'm remembering the event right. So this has happened a handful of times. There was concern when I got involved with it is this quasi DC current overheating transformers and destroying them, melting them, if you will. And there's also concern about what this quasi DC current induced by GMD would have in power system protection. That's how we got involved. Done a lot of research in this and spent probably more time than I should. This question keeps coming up. I don't know, probably every couple years or something like that. But what I can tell you from all our analysis and working with transformer manufacturers like ABB and others is transformers are designed differently than they were in the Quebec. So they're pretty tolerant. They're designed to get hot. They can. Our products have what happens with this quasi DC is it creates harmonics in the power system. And fortunately, we're already measuring harmonics. There's some power system protection we like to do when we're measuring these harmonics. So we can detect when these harmonics are happening that would be induced by GMD. We can raise a flag. It's like, hey, you better be monitoring your transformer if you think it's going to get hot, and you can pull back power. Or we can say, you know what, you're actually getting the transformer too out. We can take it out of service. And remember, power systems are designed where you can lose an asset and still keep the lights on. The other thing that you need to know about the GMD is it is really a function of when the coronal mass ejection happens, right, and then it hits the ionosphere here, right? They come in waves, and for the GMD to couple as tightly as it can, it needs to be, in alignment with the power lines. And if you're off, right, if you're getting, not in line with waves, you're not going to get as much induction into the power lines, right? So there's a lot of things that we're talking about the sun. The stars need to align, right, to get this perfect Carrington, event like to happen. So there's a lot to have happen. We had this great. It was beautiful. I saw tons. I wasn't in town. I was traveling, but I saw the pictures here in Pullman of the Northern Lights
a couple weeks ago.
Yeah, it was beautiful. You're right. There's the greens and everything.
Right.
The lights all stayed on. My alarm clock or the alarm clock at my kid's house went off the next morning. Right. She got up. The world was still here. Things we need. These are all things we need to pay attention to. Right. But there are a handful of organizations. Right. That says this is the next doomsday thing. And it's like, well, something we need to pay attention to. We've got a good handle on it with the technologies. The way transformers are built, they're pretty tough. So this is not keeping me up at night. Right. We got a lot of other things to take care of.
All right. Next question is from Luis. You mentioned this a little bit in the answer to question number 1, but do you think inverters are the future of energy, and how can we avoid a lack of inertia or maybe mitigate it in an electrical system with a high penetration of inverters?
So I think inverters are in our future. I'll say that. There's no avoiding it, right? They're going to be. We'll either have these inverters coming from solar panels and wind turbines. When you have those, the things you need to have to complement those IBRs is a battery, and battery is going to have an inverter front end to connect to the grid. So we're going to have these inverter-based resources all over the place. So, we mentioned earlier, they cause some challenges with traditional power system protection because they don't behave like big synchronous machines. So we'll have to come up with, some different ways. Maybe, Bogdan Kostiny wrote a great paper on how you manage or how you protect systems with high IBR integration. Go out to our website and read it. It's really interesting. He'll argue we need to, instead of tailoring our protection to the nuances of these big machines, and with the integration of IBRs, let's back it off a little bit, open things up a little bit, be a little bit maybe not as sensitive, but certainly much more reliable than our traditional protection. So there's lots of ways we have to solve these IBR problems. I guess my concern is the reliability of these things. Right. The sun doesn't always shine, the wind doesn't always blow, right? And batteries these days, while they're large, right, they can be 4, 8, 10 megawatt batteries. They're rated in 4 hours. So for peaking, right, to kind of manage, everybody's coming home down in Southern California, they can really help out with supplying some power. But hopefully everybody's going to go to bed at 8 or 9 or something, or stop doing their laundry, right? So that we don't exceed that 4-hour window. I get a little bit concerned, like here, if we had a pressure inversion, there was no wind, it's really dark, that we're going to run out of that 4 hour. And now what?
Right. Now it gets real dark.
Yeah. That's why I got a 48 kilowatt generator at my house, right? I can go for at least 8 days on that thing.
Okay. The next question is from Michael, and I can think of a couple directions. You could take this one, so I'm interested to hear your answer. Okay. Is cold fusion energy something that SEL can be a part of using our equipment or technology?
So let's break that up into 2 parts.
Okay.
Right? There's fusion versus the fission that we're all familiar with, right? That's what most of the reactors, all of the reactors right now that are in production run, where we tear apart the atoms. Fusion is we smush everything together. There's this idea, and you probably, if you read science journals or even the Wall Street Journal, right? Cold fusion, this seemingly easy way to do fusion, has been in and out of the news for years and years and years. And somebody to write a paper, hey, we finally got a breakthrough where we got more power out than we put in at, some colder temperatures and whatnot. But after some, analysis and peer review or something, they found out it's like, your experiment was wrong, right? That's, I think, being kind to those results. So I am very skeptical of cold fusion. I'm not saying it's not going to happen or it can't happen, but
it's not tomorrow. Is what you're saying?
It's one of those jokes, right? And even fusion's the same way. Fusion is always 20 years away, right? Doesn't pick any date and time. It's always 20 years away. I will say though, there is some interesting fusion work going on with a handful of different companies. One over in Seattle, I think it's Helios. Remember that? What's it? Helion? Yeah, Helion. They're doing some really interesting stuff. It's still not, commercially viable, and they're a way off. But it's an interesting approach to fusion. I do think at some point we're going to get somewhere with fusion. I don't think it's going to happen in the next 10 years or 20 years, right? If we're talking about nuclear energy, right? I think I'd look more at SMRs and whatnot. Now, of course, SMRs, we still need to get some of those online for the first time. We're not there yet. So
right.
There's still some more work to do in that area. We had the Westinghouse AP 1000 folks on one of our podcasts a while ago, and they just finished one in Georgia, the
right.
Vogel ones, right? And people are going to say, well, that was way over budget. But you know what? The life of those things is 80 plus years, right? So it's not like a 10-year asset. So it's like, yeah, we went over, but man, it's going to be producing power for a very, very long time. They're also building, well, fortunately, unfortunately, depending how you look at it, a whole bunch over in China, way more than we're building. Their biggest impediment to being more cost effective is they only get to build one every 10, 20 years or something like that. If they could build, at a much higher rate, the economies of scale would come into play. They'd be able to build more for cheaper. It'd be a wonderful thing. And I'm all in. Let's build some big nuke units.
It has been fun to see how involved we are in the nuclear industry. Like you mentioned SMRs, microreactors. I think, again, some of this growth that we all expect is driving a fresh look at nuclear energy, which I think is awesome to see. So,
how many people in the U.S. have died as a result of it?
I believe 0.
0 would be the right answer,
yes.
Right? And then the other thing I think about is the Navy is probably running between submarines and aircraft carriers, probably, I don't know, 100 plus, certainly, probably more. I haven't done a check. These reactors literally are being run by 20-year-old kids, right, and they don't have a problem, right? This is like, we got 20-year-old kids operating a moving reactor. This thing is like going all over the place, submerging and surfacing and stuff like that. It is amazing.
Yeah, it'll be interesting to see what this looks like 5-10 years from now. Okay, so the next question is from Cassius. With recent and not so recent hurricanes, we've seen damage to power grids and infrastructure that takes weeks or even months to repair. Has SEL made any attempts at hurricane-proofing our devices? And if not, is there an ongoing effort to do so? So this reminds me of a call I got from a customer on the Gulf Coast once, back when I was working in Georgia. And this customer asked for a new recloser control. I said, okay, tell me more. What happened to the one you have? He said, well, storm surge reached 10 feet and it's just not there anymore. It's just gone. It's in the Gulf somewhere. And so he needed a new unit. So what's your take on this? What is the impact of hurricanes on our industry, and how do we help with that?
Well, I'm going to argue, right, and I'm sure I'm biased on this, but we probably build the most rugged, reliable products there are. Now, can you submerge them underwater? No, we did not design them for that. But when it comes to vibration and, shock, electric, static discharges or other kind of electrical impulses and stuff, our devices are rock solid. They operate from minus 40 degrees to plus 85 degrees. So really brutal environments. I've got returned units that have been on fire, and that there's, the outside is all melted, but the inside is still working. So when it comes to designing really robust products, we're pretty good at. Now, a hurricane, when you talk about that surge flood, right? It's like, and you're under, it's the substation's at 3 feet and the surface of the water is at 10 feet. It's like,
what do you do?
I can't do much about that. But what I will tell you is I've been to a lot of substations in the South, and they're built on pillars, right? And they're going to do their estimates, and they'll get them 10, 20, or no, probably not 20, but certainly 10 feet off the ground, right? And so they can accommodate that surge. Now, some of the primary equipment is gonna get wet, and hopefully it'll dry out, but the substation itself is going to be okay. The other thing we've worked with customers is mobile substations, right? So they anticipate I can't take care of everything, but if I lose a substation in this area, I got these lowboy trailer with like a substation on the back of it that included some transformers and probably a breaker or two on it with the substations. We can roll it out there to hook the wires back up to get something up and running as quickly as possible. And we partnered with folks like VFP who can build control houses. They have designed theirs now to be, I think it's F5 rated for tornadoes and stuff. So if you get, and they actually use it as a shelter. So if a substation person is out there, they get the warnings, right? They hunker down inside the control house. So there's a lot that goes on to harden and make systems more resilient in the event of hurricanes or tornadoes or what have you.
Yeah, that'd be a wild experience being inside there. I do remember that as part of that call is the ability just to recognize I'm part of this customer's supply chain and I can get him a new one within a couple of days was a big deal. So yeah, even beyond the product, being able to do that delivery and make that happen quick instead of making him wait for 3 months or something like that.
That is a good point, right? With our 5-day, and you got an emergency, we'll probably build you one tonight, and if we have to, we'll put it on one of our airplanes and fly it out to you.
Yeah, it's been done. All right. Okay, next question is from Nehemiah. So so for those listening, SEL's mission statement, which we all know, and it's kind of a guiding light for us, is making electric power safer, more reliable, and more economical. So Nehemiah's question is, with all the tariffs arising globally, how can we continue to strive to make power more economical for everyone?
Well, there's a lot of things we do, right? And first off, tariffs are certainly an interesting challenge for all U.S. manufacturers. Maybe I'll tell this story. Why not? We got some time. I'm having fun. We belong to the National Association of Manufacturers. It's a U.S. trade organization for folks that build stuff, right? And it could be anything from buildings to electronic equipment. SEL, we import a lot of product that goes in our devices that we build here in Pullman, Washington. And then we take those finished products and ship those around the world, right? And we love sourcing things as parts as close as we can to home, but there's stuff that we need to get from Taiwan, like microcontrollers and whatnot. And many of those devices are subject to tariffs, right? So we have to pay them coming in. So we have to pay that tariff, which we're doing, and just as a side note, if all the tariffs, right, and this changes daily, but if all the tariffs that were enacted or proposed to be enacted would cost us about $145 million a year in tariffs. That is a lot of money.
Yeah, I don't like hearing that number much at all.
I know. But that's just what it is. I didn't put the tariffs in place, right? But that's one of the economic factors that we have to deal with. But I had the opportunity to go talk to Jameson Greer, who is the U.S. trade representative. He reports right to Donald Trump. And as part of this NAM delegation, saying how are tariffs going to impact you? And I was telling him this story, right? It's like, hey, we're a U.S. manufacturer. It's exactly what the president wanted, right? It's build stuff in the U.S. It's like, well, we've got 5 factories here in the U.S. where we're building products and then shipping those not only to our U.S. customers but around the world. We've got to be this model of what done looks like for U.S. manufacturing. And, the trade representative said, yes, yeah, that's good. Thank you very much. And then I said, but here's the deal, right? I'm in the process that business is going really, really well. We need to design or build a new factory, right, for additional capacity. And he goes, oh, that's great. And I said, Mr. Representative, they call him an ambassador. I don't know why the trade representative.
That's interesting.
Yeah, Mr. Ambassador, here's the thing. If I was a smart businessman, and I used air quotes, what I would do was build our next electronics factory, not in the U.S., but outside the U.S. to avoid bringing these parts in and paying a tariff. I would use that international electronics manufacturing to serve all my global customers. And then because I did that, I'd freed up a bunch of capacity inside the U.S. So the smart play for SEL would be not to build another manufacturing factory in the U.S., right? And he was very quiet at that point, and I saw all his aides writing stuff down as fast as they could. It probably didn't dawn on them. I don't know why it didn't. That is a viable strategy for a company. Now, I'll close the story on that because we actually did have to pick a site for selection, and we didn't do it outside the U.S. We decided to do it inside the U.S. Hopefully, these tariffs are going to figure themselves out. I don't think very many people win either way with tariffs. It really is a tax on a company, and I think we'll come around at some point where we can get rid of the tariffs altogether. But in the meantime, we're dealing with them. So one of the things we can do is be more productive when we use less people to build more stuff. Right, is one strategy that saves us on some of the labor costs. Source our parts closer to home because there seems to be less tariff cost with those things. But, we have tariffs, we have inflation, other things. At some point, we're just going to have to raise our prices, right? And that's one way. And, if you're on the receiving end of that, it's just, well, I don't want to pay more for stuff. But all of us right now are paying more for stuff, whether we like it or not. And I do take the perspective that is, well, I don't want to pay more stuff. What I do want to do is have a very reliable supplier, right, that is going to be there through me. So if I got to pay another 3, 4, or 5% or something, like, I'm willing to do that, right, to ensure that I've got somebody that's creating products, standing behind their warranty, innovating, creating new products, well, whatever it might be. So it's kind of where we're at right now with tariffs. We're doing everything we can not to have to increase prices, but sometimes you just end up having to do that.
Yeah, I understand. Okay, so we've dove into some technical stuff, did a little bit of tariff stuff, a little bit of policy stuff. So I want to go into some a little bit of a shift of gears, and I'm running this one at the moment. So I got the first question. I think that's my plan here. So this is from Bryan. So you at one point in your past ran research and development here at SEL. What is a product you were heavily involved in making that really took off, that far exceeded your expectations, or maybe just used in an application you did not plan for, you didn't expect? Why did that happen? And what can the entrepreneurial or competitive side of most of us listening to you learn from that?
So I'll give you 2 examples of something. So this is back in the summer of 1999. I got a phone call from Ed Schweitzer, the founder of the company, and he goes, "Dave, I want to build this product. We had this technology called mirror bits, and what it did is it transmitted through a fiber optic cable 8 data bits about every 2 milliseconds or so, right? So back and forth, you'd be transmitting and receiving these data bits. And it was originally designed for doing power system protection. They have these things called POTT, which is a way to send a signal to another relay to say, hey, it's okay for you to trip, or they have a blocking scheme that sends a bit to it. It's like, nah, don't trip. And that's what this communication protocol was really developed for. It had the idea, though, it's like, what if we used it just to bring in I/O from into the substation from a device out in the field without having to run a bunch of copper wires, right? We'd condense all of this I/O. Is the breaker open? Is the breaker closed? Is a disconnect switch open or is it closed? Bring all that information over a single piece of fiber. Saves people a lot of money from having to pull copper cables and wiring stuff. Is a great little device. Ed said, what do you think? And I said, hey, that sounds like a fun idea. And he's good. You got 20 days, you got 2 months or 3 months to get it done. I want to be able to talk about it at our big trade show we do at the end of October every year. And I said, well,
sounds like plenty of time.
Yeah, it's okay. And it's one of those things. It's like, I didn't even know what I was signing up for. I didn't know which processor I'd use. I didn't know how I was going to do anything. Ended up doing it, right? I made the deadline. But it was really fun, right? I got to do everything. I write software, do the hardware. Then, I was counting PEMs that you stick screws in to see how much this thing would cost. It ended up being a great success. I just looked at the numbers. This was like, we did it 20 years ago. We still sold $5 million worth of this product every year. So it turned out to be really a successful product. People instantly understood what it was for, brought a lot of value to their solutions. But I really thought it was going to be a device that just picked up inputs and outputs in a substation yards. And you asked me, it's like, how do customers use it that you weren't expecting? I was out in Maine one time, and what they wanted to do was upgrade substations, right, from electromechanical to digital. But they had a pilot wire scheme. I was talking about, sending, trip commands back and forth between substations. And they wanted to put in, microprocessor-based relays that could do that kind of technology. What they ended up doing was taking a 2505 and wrapping the contact outputs of these electromechanical relays that were saying, hey, it's a forward fault, it's a reverse fault, using the 2505 through a multiplexer to send that to the other substation that you just upgraded with the new microprocessor-based relays. So that's how they're able to integrate and take advantage of the new capabilities in these microprocessor-based relays using a 2505 to essentially translate the signals they were getting out of these electromechanical relays that didn't have any communications
So
at all.
At one substation, they had electromechanical relays.
Yeah.
At the other substation, they have microprocessor-based relays, and they talk to each other
via the 2505.
That's cool.
Yeah. So I never anticipated it. That was a great solution. It was like they're pretty smart. Another one I was more in the like project manager, not doing design or something like that. Was a product called our 651R. It's a regulator control. So if you're driving around out in the country, you'll see this gray box at the bottom of a power pole. Up at the top, you'll see this big mechanical structure. You'll see wires coming in one end of it and wires leaving the other one. That's essentially a mini circuit breaker at the top of the pole. And these recloser controls sit at the bottom, and they're measuring currents and voltages, and they detect if there's a fault, and they'll go ahead and open up that recloser, right? And then it's called a recloser because 90 or 87% or 92%, whatever it is, faults are single phase, and all 97% of those are transient. There's not a permanent fault. A branch got into something or a squirrel or something like that, right? So it's okay to close the circuit breaker back in after you wait a little bit of time. We built this 651R that was, I'll say, it was way ahead of its time. The project was really, really hard. We did some really clever things, and a lot of people worked on it. And, sometimes it felt like we did that project twice. When I talk to people, hey, what was your favoriteest project? And they tell me, oh, it was a 311C or something like that. I say, okay, tell me what was the project you hated the most. And back in the day, it was the 651R. It was really hard. It was complicated. The project the product is not necessarily complicated. The project to get everything done was really challenging. Now, you fast forward today, right? I ask somebody, well, which product do you love? And they'll say the 651R. It is, customers love this thing. Our backlog on it, I don't even how many days. It's probably 60 days or something like that, at least 24, 25. And it should be down at like 10. We've got so many customers wanting to buy it. And they're applying it everywhere, right? Originally, it was supposed to be for like long distribution feeders. How do you break stuff up? Now they're putting them, really close together, and we have this high density coordination to keep the lights on and KD and safety. So you talk about customers coming up with new ways to improve their customers' lives with our products. This 651R is just a fabulous example of that.
That's awesome. So my background is in automation products, and we have historically been similar in, size as far as how we serve our industry to those recloser control guys. And every time they beat us in any measurable way, they become pretty insufferable. So the competitive side of all of us tends to come out around the 651R for sure. Okay. Next question is from Nicole. Love that SEL is creating content for internal and external listeners. So, Dave, who's been one of your favorite external guests that you've hosted on the podcast, and why?
I'm kind of chuckling because Nicole is my wife's name, and it's not her. It's not her that asked the question, but maybe I'll give her some credit for it. All right. Well, now I got to remember what the
favorite external guest and why.
The folks I had on from the Westinghouse, the AP1000 was they were fabulous.
As a listener to that episode, you don't get to hear into that world very often.
Dr. Luca Oriani. Yeah, he was fabulous. He's a great engineer, but man, what a great salesman too. He was energetic and really, really understood his product and the applications, and how we'd be all much better if we could build some more of his AP1000s. But we also had a lot of fabulous guests. Bryan, that's not a fair question. Come on.
I didn't ask it. Nicole did. Okay. Thanks for the question, Nicole. It's a good question. Giovanni asks, what is the most challenging part of your job and why? That's a hard question.
Most challenging. It's probably the same as everybody else's, right? It's time management. What am I going to spend time on? And then, the converse of that, what am I not going to be able to spend time on? I like to say yes.
So do I.
Right. And the challenge is you can only say yes so many times before you're out of time. So figuring out, what I should be working on and not working on. I get yelled at by Joey Nestegard, our executive vice president, all the time. Well, he'll come in and say, Dave, should you really be working on that? Right. And I'm having a lot of fun, right? We're designing a product, or as we like to say, picking resistors and stuff. And he goes, is that really moving the needle today? Don't you have, 6,999 other employee owners that can help you out with that?
So you're saying the most challenging part of your job is the most challenging part of my job when I was an intern? As the president of an 8,000 person employee company.
Maybe it's a little bit different. Maybe it's a little bit different.
It sounds the same to me. Okay. Next question is from Josiah. So Josiah's he's a huge fan of the Schweitzer Drive podcast here. He's listened to a few episodes more than once. Definitely resonated with the latest episode from a material standpoint. He's curious to know what's the story behind the podcast. So what gave birth to the podcast? What did the journey look like from ideation to execution, and what do you think the road ahead looks like for it?
That is a great question. And here's really the genesis. If you go look at the first handful of episodes, it was me interviewing Ed. Right. And you might ask yourself why. And I've had the opportunity to work with Dr. Schweitzer for 30 plus years. Really closely, right? And what I have said is Ed is certainly first and foremost, he is probably one of the smartest engineers I have ever met or ever worked with. He is phenomenal when it comes to power, digital design, analog design, RF, all of this stuff. He is a master at that. But he's also a fabulous marketer. He's also a fabulous businessman, right? He is a very, very unique individual. And I got to thinking about it. Kate, how long ago did we start these things? 4 years ago? 6? Oh my God.
It's been 6 years?
6
years?
Up season 6.
Wow. So, time flies. I thought 4, it's 6. How do you share? That's great, right? Time flies. This is awesome. Kate's over there laughing at me now. I have all this benefit of working with Ed. Wouldn't it be cool if we could share with a broader audience Ed's stories, right? Let them get to know, at least in some small part maybe, what I've got to experience. So we had podcasts on business, engineering, principles of operation, all of these great things. And that's really, really what kicked it off. This idea is like, man, how do we, he's an industry giant, right? And depending on your perspective, he goes to IEEE meetings. He's a rock star, right? Everybody wants their picture and him to sign, I won't say what they signed, his hat or something like that, right? It's fun. I don't know what rock concerts you go to, Brian. But anyway,
let's keep back on me fast.
Yeah. All right. No, it's and sure. So and then once we started doing it, we had a lot of fun. We had a bunch of more internal people that we interviewed with their perspective, sharing some of their expertise and whatever it might be. And then it just kind of blossomed into, hey, let's get some outside people. Let's start doing this. And on a personal basis, I love sitting in that seat being the interviewer, right? Because I get to come up with all these questions and I get to have great conversations with really, really smart, interesting people. So for me, it's a load of fun. Now we got Kate and Blake back here that have to do all the production and organize everything. And I'm not a reliable host because I'll be traveling and, something will come up and I'll just disappear for a few days or something like that. And they'll have to scramble to reschedule everything. But it's been a lot of fun. And if people have ideas on who we might want to talk to for a podcast, if they're interested, send them in to me or Kate. We'd love to see if we could maybe integrate your idea into a podcast at some point.
Awesome. Okay, that we have one more question.
All right.
I've got a co-host that's going to ask it, though. I don't get to ask it. So we're gonna play this real quick.
Man,
Here comes your question.
Mr. Whitehead, why do birds never get zapped on power lines?
Wow. First, she called me Mr. Whitehead, so she must not know me too well. Please call me Dave if I ever get to meet you. Well, here's the thing. There's this thing called potential, and I'm going to need to make sure I think about if I had to tell my mom this, because I bet, what was it, Ava?
Ava asked this question.
Yeah, Ava, right? Ava and my mom probably have the same background in electric power systems, but let's think about potential as a step.
Got it.
Right? And if I'm standing on a step and I have both feet on them, I'm perfectly fine, right? I don't fall down, I don't get hurt. But we can think about potential as like a really, really big step. And if the bird, if it's got both its feet on the step, is going to be perfectly fine. The problem is when the bird goes to take that big step and it's farther than this, not a great analogy, but it'll be okay. He takes a really big step, he's going to fall over and get hurt. And that's why if you see a bird on just one line, it's like he's standing on just one solid step. Now, if that bird were to take a step to the other line, that's like stepping off the cliff, if you will. And that's when the bird would get electrocuted if you were to touch the other line, because the two potentials are far apart. And when they have a potential difference, that's when current can flow and things catch on fire and whatnot. How was that, Brian?
That sounds okay. So what I heard there is as long as that bird is standing on one line, not two, not three.
Yeah.
One line.
When squirrels have problems, it's because they touch two lines.
Two lines.
If they just stayed on the one line, that's why you can see them scampering down the one line. They're going to be okay.
They're okay.
Don't go to two lines.
I think that's a great answer.
Don't hit three lines.
I think that would be impressive. I think it's a great answer. Okay, Dave, this has been awesome. Thank you for allowing me to do this. Thanks for answering these questions. There are more questions, so we may have to do another one of these.
All right,
fun to ask.
I'm ready.
Thanks for taking the time to answer them, and thanks for.
Hey, you're a great host. You know, if you're ever looking for another day job,
you never know. All right. Thanks, Dave.
All right, thanks, Brian.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.